How's this? Is that good? All right. Well, good morning, everyone. So thank you for the introduction, Pushpa. So yeah, I know we already heard a number, I think 3 talks, which were taught in some way or form were titled machine learning or deep learning in particle physics. I told this one. So I won't go through the trouble of repeating all the same things, even though I will reference and I do intend to build upon what was shown in the other talks. So hopefully you've seen them, and if not, maybe if you need a refresher, you can go back and have a look at them. So my name is Sergei Gleyzer, and I will try to make this somewhat more of a high-level, broad overview talk. And I thought about how to structure this talk, and knowing that there was going to be other talks, I thought that instead of focusing on the answers, what was done, and that sort of thing, I would like to sort of frame my talk more in the form of questions. Some of these we're trying to answer. Some of them don't really have any answer yet. And more transition into sort of idea, when you have a question, how are we trying to do this now? So don't take any of the ideas there as the final answer. That's sort of my message. So none of these things are the final answer. Some of these are just baby steps in the direction of an answer. Some of them are a little bit more further along. And I'll put in the context of what the community is doing. Where are we headed? And eventually I'll get to sort of what are we doing as a community as well in this area. And where I think we're headed. So, okay, without further ado, let me start with where we are today. Right? It's good to sort of look back and see where we have been in the past, where we are today. And the story is that right now we're really at the place where these algorithms are, in many cases, in many of the applications that are relevant in HEP, they are the default. Why is that? Because they've outperformed the other algorithms, right? It's a very quantitative thing. So if an algorithm performs better, there's some way to quantify it, then there is a good reason to use it over other algorithms, right? We're scientists, so we base our things on quantitative measures. So things like identifying objects. You've seen a bunch of talks on that area. That's basically classification, right? So the first 2 things here, the identifying objects, whatever the objects may be, electrons, photons, jets, B quarks, whatnot, right? In some cases, more complicated objects like tops, and Higgs, and boosted things. So in this particular area, which is classic, well, pun not intended, classic classification, which is basically you can use machine learning algorithms many times basically out of the box. They have outperformed other algorithms that we've thought about in the decades before that. The other type is, of course, another classic case of classification where you actually do the same thing but on an event level basis. So when you have a different process or several different processes and you're trying to extract one of them that you're after, so let's say some sort of a signal and you have a number of backgrounds and you want to separate them as far away as you can, very classic scenario, and there naturally performs really well. The other type is basically using the same kind of algorithm, but with a remember, all these algorithms, all they really are is just a fancy way to minimize some sort of a cost function, right? Some sort of a loss function, which is baked in the algorithm, right? So this algorithm is basically like a baby, which is learning from the data you're giving. In the case of supervised learning, you've got labels, and you have known answers, basically experts, or your understanding of the nature or universe, whatever it is you put in your Monte Carlo generator, tells you that that's what your object, that's what your physics should be. That's what you should see when these objects travel and interact with the detector, and that's what you find. And in that particular case, when you give it the answers, these algorithms learn, and they do it by minimizing this cost function, by basically minimizing what's called the empirical risk. And that risk, no matter what type of algorithm, even though most of the focus has been in this particular workshop on what is hot right now, meaning deep neural networks, but in fact, this is something very, very general. And this particular form of the cost function, the squared form of this cost function, is actually general. It doesn't matter if you're using deep neural networks, boosted decision trees, or whatever else. You're still minimizing that same form. How we arrived at that is rather empirical, and there's other forms. It doesn't mean that we should stop there. It just means that it works. And a lot of this is empirical, meaning most of the time we first figured out that it worked and then understood why it worked. It took a decade to, in between those 2 things. And in some cases, we still don't understand why things work. So that's an important thing. But ultimately, you're still minimizing some sort of a loss function. And the interesting thing is that you can use the same algorithm that learned in the case of classification to separate two objects. You can use the same thing in the case of regression to basically estimate some continuous function. It's been mentioned before, neural networks happen to be functions of a particular form and type that can do that. Now, what no one really tells you is that, well, actually, this was also mentioned that, how complex in terms of the width and how many nodes and things you need to actually do that. And finding that optimal function that does this perfect sort of regression and learning is not an easy task. That's computationally intensive, which is why, in many cases, by going deeper, in the case of deep neural networks, you're able to end up with, even though it seems like you have millions of parameters, you actually do end up with something maybe simpler and less time-consuming to arrive at a good solution than if you did this with a single layer and a brute force and that sort of thing. So, but the point is that you can use the same algorithm to estimate continuous functions. And we have gone really far with using this. For example, we've seen tremendous improvements in particle physics in particular, where we try to estimate some continuous functions, a single dimension, in some other cases when you have several of these so-called targets, where, for example, in the case, by the way, all these things have been applied. This is now 5 years old, rather, but this is Higgs discovery plot and Higgs to gamma gamma from CMS, and all of these ideas, which at the time seemed still relatively relatively competitive and new and needed to be validated versus other algorithms, they did outperform them, and they were used, and they helped us get to these nice results in CMS. But what's important is that nowadays, this is basically the de facto standard. But then what's really crucial is that whenever you found an object like a photon, right, which deposited some energy in the colorimeter, you're able to apply these algorithms to regress on that energy. Whether you train in some Monte Carlo and you look for something that's true versus measure, and you basically try to minimize your error, improve your resolution, basically improve your detector, do better with the same amount of information. Ultimately, it's a game of minimizing errors, and in this case, it helps. So the point is that in these two sort of main applications of machine learning, meaning classification and estimation of continuous functions, we have been able to ride this wave of machine learning to get good results in that. But that's somewhat of a low-hanging fruit, actually. So a lot of this is really expanding now to other areas, and you have seen talks about that. So by that I mean also things like weakly supervised learning, unsupervised learning, and basically just applications, to simulation or generating models and all sorts of things. But it's more of applying to different things, right? And a little bit more than just this sort of vanilla classification case. Okay. And also, of course, things like trigger, et cetera. These are basically more applications. Now, looking into what are some of these sort of big questions, and how do you look at these things? So one important question, and then you saw this, in the other talks by Daniel Weitz and Kyle as well, is this idea that we're really starting to embrace now and trying to see whether we can fully exploit what we have in the data. Can we fully exploit the detector that we have? And historically, we've been really focusing, our analysis and stuff really on this area, right? So basically, this is where we baked all our knowledge that comes from, millions of detector channels. Some of them don't have anything useful in them, but the point is that we've reduced things to a really, really small number of variables on which we also try to apply machine learning, right? That's sort of what we've done in the past 2 decades or so. But then more recently, really in the last few years, the push has been really to go from right to left, right? So the idea is actually to see whether you can use some of the actual low-level data, low-level features or whatever, variables. Feature is just basically a variable to be able to build a model that actually goes around and doesn't go and necessarily perform all the other reconstruction algorithms which we've put in, which may be lossy in some way. Right? So we're trying to re-examine whether we can actually do better in some of these things, whether we're able to better identify single objects, whatever they may be, jets, photons, electrons, and so forth, from which we can then build physics observables. Now, as was mentioned yesterday, you can really do this at every different stage and see whether you can improve. But kind of the holy grail, right, is to go from the very left to the right in this case and see whether you can do better. And where we are today is really nowhere near this, right? There's only some first attempts at this, and even though they're very promising, it's not clear that this is something that's going to really revolutionize what we're doing, even though it has high potential, and it might, right? So an example of something you may have already seen in this conference is a talk by Michael Andrews, which shows this so-called end-to-end learning, meaning going from left to right, or even from here to there. And the idea is that in the simple case that was shown there, which basically uses one detector as basically an image, and it looks at photons and electrons, which is basically just purely, without using tracker, anything like that, purely, just purely electromagnetic information, shower information, where traditionally we build up things like, photon electron shower shapes, electromagnetic shower shapes, and then we use those to identify, those objects. The idea here is you go directly from the digitized and reconstructed hits, and you try to do the same thing. And the interesting message here is that in the case when you had single electrons, single photons, you end up doing better than traditional reconstruction algorithm. What's more interesting is that when you start having, more than one, you look at the performance is just really fantastic, even better than, a little bit better than what you would expect. But then when you start looking at things like more physics-related applications, no, there is more things to be done. Now, this is all, again, simulation. A lot of stuff needs to be done to show that this really works on data. But these are baby steps in that direction. And this is really an exciting area, and this might bring a lot of interesting things in the future. So I would keep an eye on this end-to-end learning idea. Okay, so in machine learning, from my point of view, is in particle physics and many other sciences, the real challenge is defining the problem. Once you're able to define the problem, then you can find the appropriate tool to solve the problem. So that's really one part towards getting towards some sort of an answer and solution is properly defining the problem. And in many cases, that means you need to figure out, given what the problem may be, what is the appropriate algorithm that might help you get to your answer. So in that many times is a challenge. And you really should. This is really a two-way street. How do you map the problem to the algorithms, vice versa? Sometimes new algorithms come along and figure out how to use them if you really want to explore. So this is really one of these sort of challenge. And a connected challenge, when you're on this journey, is really, if a problem can be already expressed as something which has a known solution, right? Then you can go straight to applying that solution. If it doesn't have a solution, then that means you can go and find it, push the boundary of the knowledge of what we have, and maybe even help others along the way. So when we look at the first class of the problems, where there is some already known solutions, problems is if you can define your problem or a challenge as something like an image problem, right, or a video problem, if you want to think of it as 3 dimensions, and there's some time of evolution. And the idea is that there's already some really excellent techniques, like convolutional neural networks, in the field of computer vision. And what you can see, obviously, in this conference and maybe over the past year or two, is we've gotten pretty far, and there's a high degree of success when we apply this idea to a problem once you're able to state it in that way. Right, so we can treat our detectors and basically imaging colorimeters, when it's colorimeters, or even sometimes multi-channel if you start adding other channels, other detector components. And you can see this in examples of jet images, colorimeter images. If you're not strictly doing jets, neutrinos have gotten a lot of positive results from this. So this is really the case, right? You frame the problem, use a tool. You've gotten something nice. Now, what sort of things should you expect from that? So you saw examples by work by Luke and others, and this was shown in Ben's talk, I think, on Monday, and maybe reference a few other places where you basically are treating your, again, your colorimeter. You basically are treating your jets as images. You have to do some transformations. You have to do a number of things, pre-processing, to be able to do this successfully and correctly, physically correctly. But the interesting thing is that there's a lot of interesting visual information which is there, and convolutional networks really do help you in this case. Then the same sort of same identical idea really, was reused by a number of neutrino experiments. Actually, I think all of the neutrino experiments that I'm aware of, big ones, have used this idea, starting with NOVA, and others, even for the simulation of Thune and others, and so forth. And the idea is that you can, you see this sparse image, you can see what's happening, you can look for the events you want, you can treat the problem as an image. It's a sparse problem, which is interesting, but the ultimate result, right? And this is one of the first results I'm quoting here. The ultimate result is that the improvements that you get from doing this basically, is equivalent to like a 30% roughly exposure time. Meaning you've saved yourself a whole lot of trouble, a whole lot of time, and a whole lot of money, right, by running a detector. If you actually just apply, it's not really a software thing, it's an algorithmic application. And you see this time and again. Applying these algorithms really does help you do more with what you already have, right? That's really the motivation. So this is an example, and I think there's more work happening in this area, both in neutrinos and images and so forth. And just to tell you in terms of like framing the problem, the other problem was still like an image problem, right? But imagine if you had something and you had some knowledge where, oh, you know what, I have some time dimension, right? And in this particular case, we don't normally deal with this, right? Normally our events are independent. We don't have to worry about what may happen. But then there are things that do have this time dimension, whether it's your jet evolving, if you do want to consider that, that you have some sort of time evolution. Or if you look at tracks and you need to basically propagate states and things like that. And certain types of neural networks, called recurrent neural networks or long-term short-term memory networks, they can do that. So applying this particular technique in this HEP TrackX project, which is an inter-experimental project looking at tracking, applying deep learning, in this context. They've gotten, some initial results which are pretty promising. There's a lot of work to be done, by the way, in this area. This is just really the beginning, and that's really the message. Don't take it as the final answer. But there's promising results coming out of this project as well that show that these particular types of networks are useful. And there are other applications for these recurrent networks. Whenever you have this additional dimension you need to exploit, and you frame your problem correctly, you can use some of these tools. Right? That's the idea. Now, there's some really interesting deep sort of results and ideas which were explored yesterday also at the talk by Daniel Whiteson. And this question whether, can we extract features, right, that have meaningful physics automatically, right? Which is one of our colleagues who isn't here, Harris and Prosper, likes to call this the automated physicist. Right. Now, it doesn't mean we really will be will be ruled by automated physicists, really, but there may be something useful in this. And really, what the way that initially this was shown in the original paper by Daniel, and really it's an idea which we see in a few other places, is that you are able to treat, if you're applying deep neural networks, they are able to extract a lot of these features, high-level features, directly from the low-level data. Again, what you call low-level, high-level, tends to change from talk to talk. But so this is not exactly raw data or things like that. In this case, low-level really means something more like 4 vectors and momenta and things like that. So it's not really that low. But even in this case, what you see is that the red curve and the blue curve are really on top of each other. And in the red case is basically the low and high together, and the black is just the low. And they're all better than the shallow ones. Right? So the question is, what has the network learned, and how can we understand that? How can we better use that? Right? And that is an open question. And we're really, as you heard in this discussion, yes, we're really just making some baby steps in this area. Now, one way to figure this out is actually to open up the box, open up your convolutional network or whatever not, and actually look at what's happening. If you treated your problem as an image, you can go and see the images that you have at these so-called convolutional filters, which are there in the beginning. So here's an example which was shown in the talk on Tuesday, where you actually use these convolutional networks to basically try and figure out what your pileup is and to remove it. And the idea is that you have different fractions, neutral charge, and whatnot. So you basically frame your problem, right? You frame your problem in this, which is a standard sort of problem computer vision, right? So you have 3 channels, red, blue, and green. And the idea is if you frame this in this way, charge, neutral, and so forth, and you open up a filter, one of these sort of like typical filters, what you can do is actually build the mathematical function out of that and see what that looks like. Aside from just actually looking at them and figure out what they look like, right? In the case of jet images, you can actually see some stuff, right? In this case, what was shown is that this actually has some relatively good meaning behind it, right? So there's something you can do some cleaning with a particular factor, and this network figured, basically trained and learned that factor. So you can actually do that, and this doesn't mean that we understand everything that's happening out of convolutional networks. Right? It doesn't really mean that right now, but this is one way that you can try to do this. There are some other approaches, but this is one clearly easy thing to do. Okay. The other interesting point is that all these improvements in deep learning we've seen mostly in the classification context. But naturally, you would expect the same thing to work on the regression context. Indeed, it's true. And you can get an improvement in this really important case to us where we want to be able to measure, let's say, particle energy better or whatnot by regressing on this. And it shows, as this plot shows, as you start to go deeper in just a simply fully connected network, what you can see is that once you start going to more hidden layers, you do end up seeing something which has better resolution. So it does help you there as well. So it's not just the classification case. That's better. OK, now, the other question that I think is really important is how do we actually use this domain knowledge that we've accumulated over the years, right? So as was discussed yesterday, do we want to throw that away? No, we want to be able to use it best, And one way that you can do this in the context of machine learning is you can also use it to design the algorithm, right? This is the stage where you figure out, okay, what's going to be, even in the case of deep neural networks, what's going to be the structure? Is there some logical way to connect things? Is there a way to break things up? And if you look at the image problem in the channels and so forth. So we've gotten pretty far with this idea, and you can see some of these applications. Some of them come from theory phenomenology, like there's an example in string theory. You can actually put some of your knowledge. There's special types of networks where you can actually put some of the knowledge that you have in there. And an example of jet images also, you have to do a number of physically motivated transformations to be able to do some of these things, basically connection to relativity. And this idea, this is in the paper by Gio and Kyle and others, and this was discussed, I think, in Kyle's talks, where you can redo jet clustering, and you can use what we already sort of know in terms of how we do the clustering with the KT and eta-KT algorithm. You can actually use that to inform the structure of your network, right? So, for example, this was one of those structures. And these are really physics-inspired ideas, and they really help you go forward. So this is also not really the final answers in any of these things, but they show promising results so far. Now, an important thing in HEP for us, obviously, is also the uncertainty, right? And this was mentioned the other day. This is an important topic in general. Now, as you saw in the other talks, is really we're dealing with both, even though it's in the context of hypothesis testing, you can make it more general in terms of two different distributions that are coming from different processes. And the idea is that you want to figure out how to best separate them, draw the boundary, and then make some quantitative statements. And the important thing is that how do you find that boundary in many dimensions, right? Machine learning algorithms help you do that when if we can only think in 3 dimensions and imagine things in 3 dimensions, and we need to go higher. Really, that's the way to do it. But the point I want to make here is that it requires decision making, right? And a lot of our results, whether we want to claim a discovery of a new particle, whether we want to figure out whether the shape of this thing can be used for some physics measurement, also includes some decision making, and uncertainty affects that. Right? And we also, as physicists, we want to be able to add that in an algorithm. It doesn't necessarily come in automatically. So there's currently open research in both machine learning area and also in the HEP applications and how you do this. And there's different ideas. So you can see, for example, how this was done in this MMPDF talk by Stefano. How it can basically sample distributions and then see how you kind of bring it back to the classical question. How far are you going using some pseudo data? Or, as was shown in this nice paper, that these uncertainties matter. Where you make the decision, where the boundary is. That nice Lehman-Pearson lemma. So Lehman-Pearson lemma was shown where the optimal boundary is. The place where, depending if you introduce some nuisance parameter and that sort of thing, it does unknown of just one dimension. Where you draw the boundary really matters, right? And so it matters. But what's really interesting for me is that there's also a Bayesian connection here. I know Pushpa mentioned this year, one of the pioneers of both deep learning applications in particle physics. What's interesting is that also Bayesian neural networks. And what's interesting is that, if you do something like a typical deep neural network and you apply a well-known technique called dropout, there's a paper that shows that, in fact, that is something, it's approximately, what you would get if you do some, basically Bayesian neural networks and you basically have this variational inference. And the connection there is really interesting because that allows you now to, to estimate some of the uncertainties. And this is a very interesting connection because you don't get it by default, right? So you have to figure out how to do this. So these are some ideas. This is not the final answer, but I think this is more where we're going. Okay, now another thing I really liked also in Kyle's talk is the idea of a multitask model, right? Now, we're nowhere near this, right? The idea is that you have a number of tasks, you have a huge, huge model, and then it's sparsely activated depending on what goes into it, right? You could think of a big detector with different processes coming in and whatnot, parts of a tracker, parts of this, different applications. So we don't really have something like that, even though it's a nice idea. The closest thing we have to that, which is sort of going in that direction, I think, is this idea where we're trying to, rather than training single classifiers as single regressors, what we're really trying to do is we're trying to figure out whether using multi-classification approach, training a model that has a number of outputs, and applying that, even in the case when you have single ones, is showing some promise. So an example of this you can see in talk by Marcus and flavor tagging, where you use a deep network with a number of outputs. In the case of flavor tagging, whether it's a P quark or charm quark or whatnot else, there's a lot of different outputs, and it's trained in many different with many of those classes. What's interesting is that it shows improvements not just in one particular case, but actually when you compare it to those single classifiers trained on those specific cases. So it's a really nice result. And also, in fact, these improvements are equivalent to introducing a whole pixel layer, really, if you think about it in terms of performance. So it tells you that there is really worthwhile investment by doing these things. And there's been more examples of multi-objective regression, something I'm particularly excited about, and then something that's shown, for example, in talks by Luke and Lu Wang and others. And I think this idea of treating this problem as a multi-class problem is really a way to go. But we're still far away from this, right? We're not there yet, but that's a nice direction. So the other areas, I'll just briefly mention them. There's not much time. Is can we really do this machine learning in real time? Now, this is something that I don't mean to apply that this actually exists. It does not exist, right? Currently, there's no live video analysis. If you look at the machine learning area, although there is really interesting applications that could be for it, both in medical analysis, real time, robotics and self-driving cars, and et cetera. The point is that it doesn't exist yet, and we really have an opportunity to actually do this and move the field forward in this particular area because we have a need for it, right? So in the trigger system, we have very low latency, and we actually want to be able to apply some of these things on the software and hardware level because we know they could give us some improvements in performance and physics. Because really, that's the first decision, right? We're throwing away all our data right after that. So most of our data. So the better we make those decisions, the better off we are later on. So there's a number of talks. You can see a talk by Andrew Carnes and others that already first applications of this, both in the software and hardware trigger of the LHC experiments and other experiments as well. So the field is going in this direction, but the field overall hasn't really solved this. So this is where we are at the forefront. The other area was mentioned by Kyle, so this idea of likelihood-free inference and so forth. Well, we really have the opportunity to push the field forward. And by field, I don't mean just the HEP field. I mean actually the machine learning field. So the other areas that I won't go into this is obviously unsupervised learning. Weakly supervised, semi-supervised learning kind of also fit into this. But basically, the idea is you have no labels. Or some of the labels are there. You can apply this to anomaly detection and look for unexpected physics. Something you've heard quite a few things about. I won't go into this. Generative models, really exciting and actually helped, I think, in many ways to overcome some of the training problems neural networks had in some ways. Is you're able to generate a whole bunch of data which is truthful and useful. And the ideas are to apply these to simulations. This is a hot area and interesting. Optimizing, tuning lots of things. Whether it's your model or maybe tuning your detector simulation or whatnot. Here you can use things like Bayesian optimization, et cetera. Even for tuning some of the algorithms, this is really useful. So these are the interesting areas. Now, there's a quick summary is that these are all exciting, right? Lots of challenges to overcome, but it's really an opportunity to go back and examine how we've done things. Right? We have a chance to do that. And I think that I will disagree a little bit with Kyle on this one, right? And I think that the fact that we've invested a decade or more into some sort of traditional algorithm is not really a good argument to not replace it with something else that performs better. The real argument is that can you quantitatively show that it is? Can you understand it well enough? And I think that makes it just because we invested a lot of time in something. If something better comes along, we should really adopt it. So that I think that a lot of these cases are making a case for themselves to be adopted in a lot of these applications. Okay, so just a little bit of history, super quick. There was a point where people really went away from neural networks, right? And this was due to some problems in learning and connected with backpropagation, gradient descent, and so forth, also overtraining. And these problems were overcome, a decade ago. It took a while for them to get to particle physics and really get adopted. And you know, there were some tricks and ideas. There were important ideas which went into fixing this, right? It took some changes to activation functions and how you do graph propagation learning, and this led to this deep learning revolution, really. It's where a lot of these things come from. The point I want to make, and I really want to kind of leave off this part, the point I want to make is that after you figured that out, after you made all those changes and figured out how to deal with this, a lot of the success relied on brute force computation. Just because now we've had more computing power, we have these GPUs. There's really no magic sauce once you figured out those problems. And a lot of this means that you do need computational resources to get to more results and actually to sustain this progress. So the question is, where are these things going to come from? We have to budget for those things. And that's basically something I want you to keep in mind, is that you know, there's no real magic sauce. And if you do need a lot of computational power to get to things quicker and get to good results for the learning of these algorithms. Okay, so just finally, really just very, very couple words about the community part of this. In the past, you know, we had a lot of great ideas and applications already in machine learning in particle physics. There's a long history, as many of you here can tell you about. But there were really pockets of ideas, and they were living within experiments of small groups. And today, the difference with today and then is that, of course, there's a lot more popularity in this. It's a hot area. Young people want to do this. And also, you know, there is potential, because potential was really demonstrated. You know, people invest in the R&D and so forth. But now there's a more organized community around this. It's pretty large. And, you know, there's discussion platforms that exist. And this allows for ideas to go forward, jump between, you know, it's something cross-experimental, where we're not really treating this as something that lives within one experiment. You only find out when the paper is published, and you don't even know the details when it's there, right? So we're not really at that point. Now a lot of things are becoming more open. There's a lot of cross-fertilization and so forth. And the recent results really speak for themselves, right? I don't think that's really just the product of great ideas. It's also the fact that ideas are able to travel and people are able to apply them quickly. So, and we're sharing them. And I think that helps. And I think today's community is really more open, and the stuff we're doing is more open source, reproducible, and collaborative. And I think it's the ones in our community who do that. I would like to really commend you for doing that, and I think it really helps our progress. And on others, you know, I think that's really, really important to embrace this idea. So, final word about this: we have a community white paper effort going on, and this is an effort by the HSF, and you'll hear a lot more about it in Liz's talk today. But I did just want to mention that this is on the timescale of the HLLHC, next experiments. And I think here we want to really look at where we are today and where we're headed in the future. And machine learning is one of the areas, right? It's one of the areas in the present and the near future. And there's been lots of contributors to this paper, and we've shared that paper with you, the draft of the paper. You know, it's a pretty mature form now, but there's still a chance to contribute, give comments before we actually, you know, put it out in the great wide world. So it discusses a lot of the things I covered today: the applications, the physics drivers behind those applications, the resources, and, you know, how do we collaborate with the community. And these ideas of collaborative data sets, something you've seen already. You know, a number of groups have done that, and we're going towards more having these collaborative data sets and benchmark data sets that are open, that we can share with others outside of our field that can help us solve the problems that we have. And yeah, so my summary is that machine learning is really at the center of what we're doing today already. And it's becoming, I think, more and more important. And there's a lot of progress over the last few years, and where R&D is really starting to bring some physics results and benefits. However, there are still many challenges that remain, you know, in terms of interpreting models, interpreting what we're having, scalability, and also, of course, you know, how do you apply these things in data and in real-time environment. But it's an exciting area, and the community is growing. So if you or your students are not yet a part of it, it's a good time. So thank you. Sorry, I think I went just a little over time.